Good afternoon, class. Here's section 3.7, derivatives of the logarithmic functions. We have covered various forms of differentiations and formulas. Now we're going to look at derivatives of logarithmic functions. Here's the synopsis of that, which we will go over with details in a moment, reminding you of the differentiation definition. dy dx is the limit of delta y over delta x as delta x approaches u, or f prime of x is limit of f of x plus h minus f of x over h as h approaches u. Then we looked at the power rule, trigonometric functions and their derivatives, product rule, quotient rule, composite function giving us the chain rule and the extended power rule, various exponential forms and their derivatives. Now, I want to remind you of what we have learned in algebra regarding logs. So, we are looking at log x base b equals y, and the base b must be positive, can't be 1. And when so, y equals log x base b is equivalent to x equals b to the power of y. Notice, as we look at these two cases, obviously they have the same exponent, they have the same base. Now, to have a better understanding of this, let's look at this arrow, and therefore b to the power of y equals x. These two are equivalent. So as we go from logarithmic format to exponential format and vice versa, if we have an easy time doing so, then we can see all these properties. Log 1 base b equal to 0. This indicates log 1 with any base, as long as, of course, the base is positive and can't be 1, is 0. Log b base b is 1. That means if the base and the argument are identical, the answer must be 1. Log base b of b to the power of x is x. B to the power of log x base b of b to the power of log base b of x is x. These two refer to the fact that logarithmic functions and exponential functions are inverse functions. If you look at the arrow, you can see the answer here. Number 5, the product rule, log of xy is log x plus log y. All of them have the same base b. Number 6 is the quotient rule, log of x over y is log x minus log y. Same base for all of them, namely b. Log of x to the power of n is n log x. Both of them must have the same base. Very straightforward. I hope it's coming back to us. Now, when the base is 10, we just don't write it. We write y equals log x. And if you look at number 1, 5, 6, and 7, you just drop the base b and you have it. But for example, number 2, log b base b equals 1, because we know if we don't write the base is 10, this must be log 10 equals 1, and the rest of them fall. Now, natural log x base e means ln x, and we don't write it in this format, okay? I just want to make sure that everybody knows y equals ln x means log x base b base e, and it means, of course, in an exponential format, e to the power of y equals x. Again, general properties, a specific case where we are dealing with base. Notice for numbers 1, 5, 6, 7, again, you just change the log to ln. But for example, number 2, the base is b, so is the argument. Because in the case of ln, we know the base is e, then it must be ln e, and the rest of them follow. See? Also, Logarithmic functions and exponential functions are inverse functions, for example, y equals e to the power of x and y equals ln x. So if you use the same set of axes to graph them, then they must be symmetric with respect to y equals x. And this is also called the change of base formula. In this case, log x base b is log x over log b with any base, for example, base a. However, we either use common log base 10 or natural log base a. Also, notice this point, the x-intercept has coordinates 1, 0. If x is between 0 and 1 here, then log is negative. And if it's here, that means x is positive, log must be positive. So I hope everybody is okay with this. Okay, that's pretty straightforward, everyone. Now, let's look at the warm-up example. We want to evaluate the following. And how did we do it in algebra? Let's say we have no idea. We're going to say it's x, and we're going to go with the definition of a log and write it in exponential format. 3 to the power of x is 81. And we all know 81 is 3 to the power of 4. Therefore, the answer must be 4. What about log 5 base 25? Let's say we don't know the answer. We are going to go with an exponential format. According to this, 25 to the power of y must be 5. And we know 25 can be replaced with 5 squared. Therefore, 5 to the power of 2y is equal to 5. On the right side, when we don't write the exponent must be 1, 2y must be 1, y must be 1/2, as you can see it here, or understand this is square root of 25. What about log of 0.001? I'm going to remind you log 10 equals 1 has 1, 0. Log 100 is 2. Log of 10,000. 4 zeros, that's 4. Log of 0.1. 1 decimal, -1. Log of 0.01. 2 decimals, -2. This is -3. Or 10 to the power of -3 is 0.00. So I hope it makes sense to everybody. Okay. Now we want to go the other way around from logarithmic format to exponential format, and this is 5 to the power of 4625. Seven squared is 49. One-third to the power of -4 is 81. One to the power of 1/4 is 3. 1/2 to the power of -5 is 32. So very straightforward, everybody. Now, what about these two? We want to make sure that we can handle them also. Again, just go with the arrow. Ln, when we don't write the base is E. So e to the power of t must be s. We go with the arrow again. Log, there is no base. That means the base is 10. 10 to the power of q must be p. Now y equals ln x. We want to take the derivative of that, and how do we approach that? Well, reminding you that y equals ln x means e to the power of y equals x. And reminding you, if we want to differentiate e to the power of kx is itself times k. If we want the derivative of e to the power of g of x is itself times g prime, and y is like g prime, or think of it as implicit differentiation. So the derivative for the left side is itself times y prime. X, of course, is 1. So y prime is 1 over e to the power of y prime or dy dx. So if it's 1 over e to the power of y, it's the same as 1 over x. So what we proved, when y equals ln x, its derivative just flip over the argument of the natural log. So what happens? d dx of ln of absolute value of x is 1 over x. X can't be 0. I want to explain the absolute value. Remember, for a natural log, the domain is 0 to infinity. So you have to pay attention to that. But if we put absolute value, we don't have to worry about it. Needless to say, x can't be 0. What about d dx of ln of g of x? Then using the chain rule, the answer is itself. That just like that, flip it over. And then by the chain rule times g prime, and again, g of x is positive. This will cover this concept. Instead of g, we may call it just u. d dx of ln u is 1 over u du dx. U must be positive. So having said that, let's differentiate this guy. And the very first thing I want to mention, when you do logs, the first step would be to use logarithmic properties to decompose if possible. This can't be. So what is the derivative? Flip this over. ln of g of x. If you want to differentiate, flip it over. Times by the chain rule, the derivative of the parentheses, the derivative of the argument, which becomes number 5, and just rewrite it. What about y equals ln of x cubed? There are two ways to do it. I'm going to do both ways. First and foremost, just the way it is simple enough that we're going to follow that. We're going to look at the argument and flip it over. And then by the chain rule, the derivative of the argument, so times 3x squared, and of course, it means 3 over x, and we're done. However, we could use number 7, the power rule, put number 3 in front, and say, well, I'm going to differentiate this. I already know the ln x is 1 over x, so 3 times 1 over x. By the way, we are assuming that x is in the proper, domain. That means x is larger than 0. Otherwise, you have to use the absolute value. So There's really not much of a difference between the two. Both are just as easy. However, the more complicated this log, the easier to go with the second method by decomposing it. For example, if we have f of x equals ln of 2x over 2x plus 1, and we want to differentiate that, if we don't decompose the log, that means flip this over, which is not a big deal. But then you want to differentiate this using the quotient rule. But there is an easier way, which means we are going to decompose this. And you can do it in one shot. I'm going to take a couple of steps. And first and foremost, I'm going to use the quotient rule and say this is ln of the top, which is ln of 2x, minus ln of the bottom, which is ln of 2x plus 1. And then I'm going to go with number 5 and decompose this one into ln2 plus ln x. I mean, this is simple enough. If you don't, it's not that big of a deal, but I highly recommend you decompose it completely so it becomes a very easy differentiation. ln2, that's a number. The answer is 0. ln x, 1 over x, minus ln of 2x plus 1, just flip it over first, by the chain rule times g prime times the derivative of the argument of log, which is 2. And I'm going to box this. This is the only calculus step, everybody. Everything we have done has been algebraic step, and everything we'll do from here on will be algebraic step. So having said that, this is 1 over x, this is minus 2 over 2x plus 1, and the common denominator would be, we are going to take the LCD, x times 2x plus 1. And that means 1 times 2x plus 1 minus 2 times x. So the numerator is 2x plus 1 minus 2x is to cancel each other. The final answer, f prime of x, is 1 over x times 2x plus 1. Y equals 5x times ln x squared. Using the power rule, everybody, I'm going to put number 2 in front. 5, so this becomes 2 ln x. So we are using number 7, and this changes to this. And now it's 10x times ln x. We are going to use the product rule. Fg becomes f prime g plus g prime f. F prime is 10 times g ln x plus g prime is 1 over x times f 10x. And this changes to 10. Factor the 10 out, and the final answer 10 times ln x plus 1. Y equals ln x over x. The first step is to try to simplify if possible. As you can see, there is nothing else we can do to simplify it further. So we're going to approach it as, as a quotient rule f over g, which means we are going to go with f prime g minus g prime f over g squared. Remember, I've gone over the easy way out, the shorthand notation, but whatever you are used to, you can stick with that as far as differentiation is concerned. So I need f prime g minus g prime f over g squared. So f prime ln x gives me 1 over x times gx minus g prime, the derivative of x gives me 1 times ln x over g squared x squared. And this is it. I'm done with calculus here. The rest is easy. Of course, the product of these two is just 1. This doesn't change, minus ln x, and neither does the bottom. So the final answer, y prime equals 1 minus ln x over x squared for this question. All right, we want to differentiate y equals ln of 3x times x plus 4 to the power of 5. If you want to differentiate it just the way it is, you have to flip this over. Then you have to use the chain rule as well as the product rule. Instead, we're going to cut this into 3 pieces. Ln of 3 plus ln of x plus ln of this piece uses the power rule 5 ln of x plus 4. I hope no one has any problem decomposing the log. Now, ln 3 is a number. The answer is 0. Ln x is 1 over x. So we work on this piece. To do that, plus 5 remains. We are going to differentiate ln of x plus 4. First, we're going to flip it over, 1 over x plus 4. So we are using this one. And then by the chain rule times the derivative of the argument, which happened to be 1. Therefore, we have 1 over x plus 5 over x plus 4. Again, bear in mind, this is the calculus step. Now we're going to find the common denominator, which is x times x plus 4. To combine the two fractions, 1 times x plus 4 plus 5 times x. So we get x plus 4 plus 5x. We can combine these two, and the final answer, y prime equals 6x plus 4 over x times x plus 4. This is our final answer, everybody.